So today I will be talking about localizing invariants of
on locally compact closure spaces and in particular on finite level complexes. And so what I want to start with is let's recall this category. I think I had different notations for it. So like sheets on the real line, sheets of spectra with non-negative single support. So this was also at some point denoted as continuous stabilization of this partially ordered set of real numbers with plus infinity. So this was considered as a compactly assembled accessible category, and we had this construction of continuous stabilization of such categories. This was the same thing, and this was just the same as functors from real numbers, contravariant functors to spectrum, such that for any real number A, the value of this functor is the limit over E smaller than A f of T. And what I want to explain, first statement is that so take any let's say accessible localized invariant. Let's see, phi from small categories, small stabilized but complete categories to some category E, which is stable accessible category, not even necessarily presentable. Then F continuous, this continuous extension, phi continuous. Continuous extension of this invariant computed on this category of sheets with non-negative single support is 0. And so I want to explain this and do application of this. Like first, that K theory can use with products. Actually, both for small categories and for dualizable categories, but let's for now restrict to small categories. So this K theory as a functor from small stable categories can use with products, with infinite products. And second, computation of arbitrary, let's say, accessible localized invariant for categories of trees on a finite level complex. So X is a finite level complex, and C is a dualizable category. Remember yesterday I explained that this single object generates the whole category of dualizable categories under K-limits. This is one special property of this category, but another very nice property is that like everything vanishes on this category. To do this, I first recall step one. Just suppose that we don't know this Kasperovsky and Wien together. So this is due to Kasperovsky and Wien originally, but I will give a different proof. So suppose that we don't know this Kasperovsky-Wien theorem, then there is a very simple argument to show that K0 can use with products, with infinite products. So there is you simply use this Hilbert's criterion for if T is small triangulated category, and you take two objects, x and y, then the following are equivalent. Their classes are equal in K0, and there exists some Z, U, V in T, such that there exist exact triangles U, x plus Z, V, and U, y plus Z, V. I mean, this is a very nice criterion to figure out like when the objects have the same class, and like implication that 2 implies 1 is just obvious, but to see that 1 implies 2, you just use the second condition to give alternative definition of K0, and then you just figure out that you have two maps in both directions. They are tautologically inverse isomorphisms. So this is a very nice criterion, and corollary is that K0 commutes with products. So K0 of infinite products of small triangulated categories maps isomorphically to the product of K0. Just because in each component you need only uniformly bounded number of objects to figure this out. Uniform bound is 3, which is good. So K0 commutes with products. The interesting question is about other K groups. But already using this, we will actually prove that all the class invariants vanish for this shifts, this single support condition. So how do we do that? So step 2. Recall that we have this. We can describe this category using functors not from real numbers but just from rational numbers. So basically, we have two exact sequence: 0 to shifts with non-negative single support, to functors from rational numbers but with covariant functors. Spectrum, and then just the product of copies of K0 spectrum taken over rational numbers. I mean, it's you need to do one more observation to figure this out, because this condition is described using limits, and I want to replace it with a condition using colimits. So this functor, let's call it f. So f of g, if you take its component streptonic to rational number A, this is cone of the map from the colimits of p greater than a, g of b, to g of a. And basically, and because Q is a dense linearly ordered set, this functor is a localization. So Fr is actually fully fixed. So the composition F composed with F right adjoint identity. And you can observe that shifts with this non-negative single support condition, this is the right orthogonal to the essential image of the right adjoint. But because this right adjoint has both right adjoint and left adjoint, so this right orthogonal is the same as left orthogonal. Which is topologically the same as the kernel of F. So we get this short text sequence of the logical categories. And you can observe that so this category, let's call it, this is A, this is B, and you can observe that A and B are, of course, completely generated. Now I should switch. Yeah. Yeah, so these categories are completely generated, and so we only need to show that if you take compact objects, then the functor with f omega from a omega to b omega is k equivalence. I will recall what this means.
Can I ask something?
Yes.
Category in the middle, should it also have some extra condition that the functors satisfy f of a is the inverse limit of b less than a? Like you think that you
No, the category in the middle is just all functors from rational numbers to those spectra, without any conditions.
Okay.
That's the point. I mean, here we have some conditions, but we express these conditions by taking either right or left orthogonal to the image of this right object. That's the point. So we only need to show that this functor f omega from a omega to b omega is a k equivalence. So, which means there exists some functor, let's say g, from b omega to a omega, such that both compositions f omega compose g. So if it exists composition, for example, then its class in K0 of n the function should be the same as identity. So this equality in K0 of exact n the functors of b omega. And the same g composed with f omega is the same as the class of identity in K0 of n the functors of a omega. Now you can observe that we have an obvious section of this functor, so that one of the compositions is literally identity. So take g omega. So I mean, so these compact objects. So the category E omega is simply the direct sum or co-product of small categories of finite spectra. Taken over all rational numbers. And in the section, to define the section, we just need defining such a functor is the same as defining a collection of objects. Here it is by rational numbers, but it corresponds to the collection of representable presheaves, stabilizations of representable presheaves. HA is rational. So this HA is just a functor to spectra, so HA of B is a sphere spectrum if B less or equal to A, and 0 if B is greater than A. And so this representable sheaf, of course, goes to an object which has only one non-zero component, which is the sphere spectrum, which is sitting in this, corresponding to this number A. Okay, so we have, sorry, this is just G. So we have f omega composed with G is literally the identity. So what we want to show is the composition in the other direction. So G composed with f omega has the same class as the identity in K0 of n the functors of a omega. Now this might look scary because we take this compact objects in this category of functors and take n the functors, and it's just not clear what the hell is going on, like how to describe K0. But in fact, if you stop being afraid, then you can just describe K0. So we will see that position that K0 of n the functors of the category A omega is just literally endomorphisms of the free abelian group, which is direct sum of copies of C indexed by rational numbers. So how do we see that? This is like step three. We need some funny like completed additivity statement for completed semi-orthogonal decompositions. Namely, let me formulate it carefully. So take some. So let C be a small wasn't complete stable category. With infinite semi-orthogonal decomposition indexed by rational numbers. By natural numbers. With SOT, so C decomposes into A0, A1, and so on. Which means that there are no homes from AI to AJ for I greater than J. And this subcategories AI generate C as a stable subcategory. So roughly speaking, there are no homes from right to the left, and each object has a finite filtration which subquotients limited this.
Just a question. When you write functors from A omega to A omega, do you mean exact functors?
Yeah. By default, the functors between stable categories are exact. I just don't want to write exact every time. I will not be considered polynomial functors. So it's now let's consider this subcategories generated by so Bn, which is generated by A0, etc. An. So this is the subcategory of C, and we have this functors from Bn plus 1 to Bn, which is left adjoint to the inclusion. So this is basically the functor which annihilates this An plus 1 component, it's like semi-orthogonal projection. And then the statement is the following: that so consider compositions. So limit of Bn goes to some particular decay, and then we take projection to AK. So this AK is now right adjoint to the inclusion. Again, it's just semi-orthogonal projection, so it annihilates all the other components. Then the statement is the induced functor from the limit of Bn to the product of all natural numbers of this categories An is a K equivalence. So how to see this? Sketch. So let's denote this. So let's D denote by D this limit. Denote by pi n from D to An this composition. So our functors which we consider and consider inclusions. So we have all inclusions iota n from An to B given by compatible functors. So you first take inclusion of An into Bn with the same n, and then embed into PK. This function from a compatible system, so you get a well-defined function from AN to B. And then, in fact, you have also a well-defined functor from the product of AN to B. You can simply multiply this object, take the product, so it's well-defined. And now compositions, and denotes this functor by pi. So pi is component pi. So then, tautologically we have that pi composed with iota is identity functor. This is identity functor of this product of AN. But now, the statement is that the composition in the other direction, so iota composed with pi, has the same class as the identity in K0 and the functors of B. And for this, you just need to use some kind of Allenberg spindle, but the conclusion of it will be not the vanishing of something, but the equality of something. And basically what you do is you consider this functors, let's call them psi n from B to itself. And this is the composition. So we go from B to the left orthogonal to Bn to B, where each case group Bn is actually naturally included into the limit, because again we have compatible system of inclusions. So Bn is included into Bk for k greater equal to n, and these inclusions are compatible with this opportunity. You have the same orthogonal projection, so this is just right adjoint to the inclusion, and this is included. And now you simply observe that so you simply observe that you have a well-defined infinite direct sum of this function psi n, and you have inclusions of psi n plus 1 to psi n, and if you take the direct sum of the fibers, you simply get iota composed with pi. This is quite easy to check. It's almost tautological, but you just need to be careful with infinite direct sums of functions on small cases. But this is well defined. And now we simply conclude that the class of identity I mean in n the functors of B, is the same as, tautologically is the same as a class of psi 0. Psi 0 is literally the identity. And sorry, if I want to be the identity, it should be Pn minus 1 left orthogonal, and B index minus 1 is just 0 by definition. The class of identity equals the class of psi 0, which is of course the same as the difference between our classes of well-defined sums of psi n over non-negative n minus the class of the sum over n greater equal to 1. But now we have this fiber sequence, so this is the same as the class of iota composed with pi. So it's not cheating, it's legit argument. This is how you prove that you have escape equivalence. But now, this is actually a very useful and strong statement.
Sorry,
yeah.
I'm slightly confused because it seems to be that K equivalence detecting, detecting a lot of additive variance.
But in particular, localizing invariance.
Yes, I just wonder, here, are you really using it's localizing, or some?
I mean, I use short like, let me switch this. Yeah, I mean, I want, in the end, I want to know that this functor on composite object is a key equivalence to deduce the vanishing of the localized invariance here. So I'm using the localization property.
Yes, but this part that you don't use.
Yeah, I mean, of course, when I'm talking about key equivalence, in particular, yeah, I can deduce that it's isomorphic on all edited invariants. Okay, yeah. Okay. So now, let's observe some implication of this completed semi-relativity. So corollary is that so suppose that we have some inverse sequence of small categories B0, B1, B2, so on, such that each functor Bn plus 1 to Bn has a fully faithful right adjoint. So this is like very strong condition. So it's not only has a right adjoint, yeah, so this is sequence in small categories. Small and complete categories. So it not only has a right adjoint, which is already a strong condition, but also fully faithful right adjoint, without going to large categories. Then K0 of the limit of Bn is just the same as the limit of K0 of Bn. Just apply, so you simply need to apply the above to coordinate of Bn with respect to right adjoints. With respect to right adjoint functions. Because the whole limit has this semi-cognitive position indexed by rational numbers, and so if we denote by an just the kernel of our functor from Bn plus 1 to Bn, then we conclude that K0 of the limit of Bn. So because of K equivalence, this is the same as K0 of the product of An. But now we know that K0 commutes with products, so it's product over n of K0 of An. And now by the usual additivity, this is the same as limit over n of K0 of N. So this is like commutation of K0 with like extremely nice reverse limits. Normally you don't encounter so nice.
So I think probably correctly for this other criteria.
Directly proof what?
The inverse limit, the commutation of the inverse limit.
Yeah, but you mean directly proof by which means?
Just make a map both ways.
No, but still you need to prove that when you take some object in the limit, its class is the same as the class of the direct sum of this component.
Yeah.
Yeah, but I think what I explained is basically the way to do it. Yeah. And I mean, okay, you don't have to deal with the center factors, you can just deal with objects, but still you need to do something, right?
Just
yes. Yeah. So, okay, so we have this very nice corollary about the limit of this very nice inverse system. And now, so we wanted to conclude that, let's return here. We wanted to conclude that our functor f is a k-equivalence and more precisely we had this more precisely we wanted to deduce that k0 of n the functors, this category A omega, is just endomorphisms of the direct sum of corpus of Z. Basically, you can just observe that a omega. Okay, so the way to see this is you first choose some numbering of rational numbers. So choose a bijection between natural numbers and rational numbers as sets. So n goes to some an, and so let Cn inside the omega stable subcategory generated by this representable sheaves like HA0, etc., HAN. Then what you get is just that K0 of n the functors of A omega is the same as inverse limit of K0 of functors from Cn to A omega. But each of these categories is just the same as functors from linearly ordered set with n plus 1 element to A omega. And this is the same as limit over n of direct sum of copies, or let's say direct product of copies of direct product of n plus 1 copies of K0 of A omega. But we also know that K0 of A omega is simply the product over Q of K0 of finite spectra. And this is just a direct sum of over corpus of over Q of corpus of Z. And so this just if you just I mean do it compatibly with our numbering of rational numbers, so you see that this is literally an endomorphism of direct sum of corpus of Z over Q. And this is basically sufficient because we wanted so we had this section G from B omega to A omega, and we simply observed that both F omega, G composed with F omega, when you apply it to representable redshift HE, this is just HE. So the action of G composed with F omega on K0 of omega is just identity, and so its class in K0 is just the same as class of identity. So that's how we compute. That's how we prove the vanishing of all localized invariants on this category of sheet. Okay. So I guess that's the first interesting computation in this lecture course. Now we have parallel this. Yeah.
For this K theory computing with infinite products, you said K0 is an easy case, but
Yes.
if you repeatedly apply this to like calculating constructions,
you get the statement for negative, and if you use our computation, you can also prove it for all k groups. But let me just explain this okay for you. So you can deduce this result that let f from curve to E be accessible localized invariant, and suppose E has a non-degenerate T-structure. Non-degenerate means that if homotopy groups of every object or some object vanish, then the object is zero. Sorry. Suppose that we have two functors and the map between them, y from f to g. So suppose that pi 0 of f, pi 0 of phi, from pi 0 of f to pi 0 of g, is an isomorphism of functors with values in the heart, with values in the heart of E. Then phi is an isomorphism. So this is like part one, and part two is you basically deduce that K-theory commutes with products. So let me first explain why part one implies part two.
You don't have accessible for part one.
No, the only reason I'm using the word accessible is just to avoid theoretic issues. I can ignore these theories, and there's no problem for me, but I think we should be a little bit careful. But yeah, of course, I mean, it's not really relevant, this accessibility. Okay, so prove that one implies two. As already Thomas mentioned today, if you want to prove something for families of objects, a statement of the sort for families of objects, you can just assume that the objects are just the same. So we need for any set I, the map from K-theory of the product of copies of I of some small category C. So it goes to product of copy over I of K-theory of C that you want. This is an isomorphism. Basically, both of these guys are localized invariants. So just observe source and target are localized invariants of our category, and the condition is satisfied. So if this is phi, then pi 0 of phi for the standard structure is an isomorphism. This is what we already discussed. So the statement for K0. And so if you know part one, then you deduce part two. But now to prove part one, you simply use the counting construction and the shifts and the statement called shifts. So the fact that pi 0 isomorphism is isomorphism implies that pi n is isomorphism for n non-positive. So basically use the inclusion, so you just embed C into countable incompletion, then you go to countable counting category C. And that's it. You inductively, so knowing the statement that pi 0 phi applied to counting category is an isomorphism is the same as the statement that pi minus 1 is invariant applied to C is an isomorphism. and then just proceed by induction. But then, so we also deduce by the same argument that for any dualizable category C, let's use a different letter, category D, we have that pi n isomorphism for n at most -1. Just, at most -1 just because we have this shift. So we also go to helping construction. Yeah, and then you simply use we use this short exact sequence. So shifts with non-negative singular support on R go to spectra. If you think about them as shifts on the real line, then this is just sections with complex support. Let's say when shifted by 1. If you shift it by 1, then this is, in terms of functors, it is the same as taking a limit when the argument goes to -infinity. And this is localization. This is like a strongly continuous quotient function. And if we just denote it kernel by shifts with subjects strictly greater than 0, then again inductive argument plus the vanishing for the category in the middle. So the same inductive argument implies that pi n is isomorphism for all n. Well, strictly speaking, pi n of continuous extension of our map. So continuous, f continuous and g continuous are just invariants extended to the level categories. As Thomas explained for K-theory, but you can do it for any local invariant. And so we conclude that this is isomorphism for all n, for all integers. Yeah. I mean, it's convenient to phrase this in terms of universal gas invariant. So if you know the vanishing of universal gas invariant on some category, then it also vanishes for this category tensor with something. Or you can just say that tensor with something, and then applying our f or g is also gas invariant. Yeah, that's right. Okay, so that's the way how to prove this general statement. And Boris has still explained to me an argument that you can actually modify, I mean, just simplify considerably the proof of Kaspersky and Lingus, and his argument actually implies also this part 1. You can prove it without using classical categories at all, but I just find it very, like, I think it's the most conceptual proof of this fact. Yeah,
and in that case, you don't need accessibility.
Yeah, I know. Maxim already told me that. And, I don't really care about accessibility, but some people care about set theory still. I think. Okay, so now let's deduce the computation for shifts on finite level complexes. Yeah. Sorry. I mean, pi n phi continuous computed on T. That's what I want to say. So if you just take the values of f continuous and g continuous on T, then we get the isomorphism on for this pi n, where n is at most -1. This is what we deduce from the statement about small categories, right? Because we just pass to the Gaussian category, and we get the shift. So if we know the statement for small categories for n at most for n less equal to 0, then we get the statement for the larger categories for n at most -1, right?
You're inputting that you know it at I0 for complexly generated categories.
Yes.
And that gives it to you for all equivalent categories for n.
Yes. Okay. Okay, so let's do another. Let's make another observation that for any, I will still impose accessibility conditions, no matter what. For any accessible localized invariant, with relatively some accessible stable category E. So F continues computed on shifts on the same open interval, but it's convenient to consider this same open interval as R union minus infinity is zero. Basically, we just observe that there is Schroedinger sequence 0 to shifts with non-negative single support, to shifts on this R union minus infinity, to shifts with non-positive single support. Okay, well, let me just briefly explain what is Schroedinger sequence. Let's introduce some awkward notation. Let gamma be the cone of non-positive real numbers, and our sub gamma is the just a set R equipped with gamma topology. This is the term from Kashewar and Shapira book. Basically, U is open in R gamma if U plus gamma equals U, and U is open in R with usual topology. So basically, the open sets are just empty sets, the whole real line, and the race from minus infinity to and similarly. So same for R with minus gamma topology. And then you have this phi gamma from R to R gamma, and phi minus gamma from R to R minus gamma. It's just an identity map, considered as a map of topological spaces. And you also get this funny map from the R union minus infinity to the simplification of R gamma, because R gamma is not sober, because the whole real line is irreducible, but you don't have generic point. Generic point is minus infinity. So you just add minus infinity, you get this identity map as a map of topological spaces, and the only reason why I define this is to say that this is just phi gamma bar upper star. And this is and this functor is left adjoint to J lower streak phi minus gamma upper star, where J is just an inclusion of R to R union minus infinity. So it's just an elementary exercise to check that this is Schroedinger sequence, and we know the vanishing of all the classic invariants for cases with single support conditions, so we know the vanishing for again of all the classic invariants for shifts on the same open interval. Okay?
Wait, what is phi bar?
Just extending this map to simplification. Okay, so now we can deduce the computation of all class invariants without any conditions, but still accessible. For cases of shifts on finite element. Let X be a finite set of the complex. And C the lesbian category. and F is some accessible local invariant. Then F continues computed on the category of sheets on X evaluation C is the same as F continuous of C. Now we take the limit over X. So here, so in the right hand side, X is considered as an animal
Or infinity, let's say infinity groupoid. And we take the limit. So basically, it follows from what we already discussed. So so observe that for any finite cerebral complex, let's say Y, we have so F continues computed on shifts on Y multiplied by the unit interval.
Evaluation C is just the same as F continuous computed on shifts on Y evaluation C. And so this allows you to define a functor, let's say G, from, I need another, I think this, but it's also nice, or this is preferable. G from infinity category of finite spaces to E, such that if X is a finite cerebral complex, then G of X is a continuous of sheets on X in C, and we only need, so we know that G computed on the point is just F continuous of C. And we also know that G computed on the empty set is of course 0. And so the only thing left is to show that G computes with pullbacks.
You explain how to reduce this from this one?
Yes, sorry. Okay, so let me be brief.
You could do it half the speed, no? I mean, that's still. No.
Let's just say that we take universal Lucas invariant for some cardinality of shifts on the unit interval. And this is just the same as this universal invariant computed on spectra. Just because, so using the short exact sequence, you embed the semi-open interval to the unit interval, and then you pull back to the endpoint. And because we know the vanishing for semi-open interval, we deduce this. And so we get this chaotic invariance. So now we only need that G commutes with pullbacks.
You have an up also there.
Sorry?
You want to spin it up?
Sorry, of course, it's contravariant, yeah, thank you. Yeah. So only need that G commutes with pullbacks. But now we can take an actual diagram of finite cerebral complexes. Let's say X to Y is a cellular embedding of finite cerebral complexes, and X to Z is just some continuous map of finite cerebral complexes. Then we have this pullback square, so shifts on the push out on the naive push out of finite degree complexes. So this naive push out also computes the push out in the infinity of spaces, and this is basically the pullback. So we have pullback functors to shifts on y, pullback functor to shifts on z, and pullback functor to shifts on x. And and this is pullback square both in PRA and in the case of generalizable categories. Here, the reason why this pullback is the same is just because this pullback from y to x is a quotient functor, because the right adjoint is pushed forward, which is fully flexible. And now we know that G commutes with such pullbacks. So G commutes. So sorry, not G. I mean our localized invariant commutes with such pullbacks. So this is like a little lemma. So if you have some pullback square like say A, B, C, D, pullback in PRA, but also we assume that A, B, C, D are generalizable, and functors are strongly continuous. Then A is also the pullback in the case of generalizable categories, and we have the commutation of generalized invariance with such pullbacks. So if continuous of A is the final product. F continuous of B, F continuous of C over F continuous of D.
Sorry, I can read this.
Sorry?
Which message from continuous?
All functors.
All functors.
Yes. So I mean, in general, we didn't yet discuss in detail the limits of generalizable categories, and in general, given the finite limits can be complicated to compute. Already the final products are might be complicated. But if it happens that you have such functors from C to D and B to D, and one sorry, I didn't mention the assumption. Sorry. Yeah. I'm sorry for using the same letter many times.
You say the vertical maps or
yeah, let's say the right vertical map is localization, then phi is localization. Then the left vertical map is also localization, and basically the kernels of vertical maps are the same. And so this way you reduce that localized invariant commute with such pullbacks.
But the first step of the lemma is true without this, right?
Sorry.
The first step of the lemma, the fact that it's also a pullback in factorial.
No, for this you need.
I think the finite limits is fine.
I mean that if all the categories are dualizable and you're right. Sorry, that's right. But if I want to,
if you want to,
to make assertion about the best invariance, then I need this condition.
Try to summarize that again. Sorry. The first part is.
The first part is true without any condition that some functor is localization. So if you have a pullback square in presentable categories and all the categories are dualizable and all the functors are Trolley continuous, then it's pullback square in dualizable.
Sasha, could I make a remark?
Yeah.
Because so it's also true that if you have the localization hypothesis, we only know that B, T, and C are dualizable, and it actually follows.
Yeah, of course.
So no, just to say, I have to make a remark because I mentioned this in my lectures that I
Yes,
so
yes.
I didn't know the correct original reference. It turns out Sam Raskin proved this in appendix to one of his papers.
That's good.
Yeah, so it's not a trivial argument. So I wanted to.
Yeah, I know that it's not tautological. I also included the proof, but I didn't know the.
Yeah, so now that's the.
Yeah. Okay.
Many years ago.
Okay. About dualizability.
Yeah.
Okay.
Yeah.
That's good. Yeah.
I just have a question about the statement was we're still assuming phase of localization, or what was the condition for the first? What was the condition for the first?
If you don't care about localized invariance, then I just made a statement that if you have a square of dualizable categories in the category of dualizable categories, which happens to be a pullback in PRA, then it's pullback in dualizable categories.
Oh, but then became A, which
Yes. No, but I already assumed this.
Okay.
I mean, there are different statements, like the way I formulated it, well, maybe it's suboptimal, but at least in this case, we certainly know that all these categories are dualizable. Yeah. But yeah, as Dustin correctly pointed out, you can just assume that all the categories except for the pullback are dualizable, and one of them is a collision functor, then the naive pullback taking parallel will be also dualizable, and this will be also pullback square in the case of dualizable cases. I think the last statement maybe is not in Raskin, but yeah. Okay. So yeah, and in particular, this applies to our situation. So we deduce that our functor, which we denoted by G, that it's conducive with pullbacks, and that's what we needed. That's all we need to deduce. Do I have a positive or negative number of negative? Negative. Okay, then let's stop.